Okay, great. Thank you so much, Tobias, for the introduction. It's great to see everyone here at NoBugs after 4 years. My name is Nicholas Schwarz. I'm the group leader for scientific software engineering and data management at the Advanced Photon Source. And I'm going to spend some time talking about the strategy that we've developed for scientific computing going into our upgrade era and upgrade project. So, like many of the other synchrotron light sources, and SLS is of course one of them, the APS is in the midst of a large upgrade where we're going to replace the storage ring and certain parts of the LINAC and the booster with a new MBA lattice. And this will do things like provide an increased brightness up to 500 times for some instruments. And additionally to that, it's going to result in a more highly focused beam profile. But besides just the accelerator improvements, we are making substantial improvements to a number of the beamlines. So we will have 9 new or almost entirely new what we call feature beamlines, and then 15 enhanced beamline projects. And so as we look through kind of the needs and the requirements for this and what the future is going to look like, it's really clear to us that scientific computing is going to be critical for the success of those instruments, for the scientific success of our mission. So as we went ahead developing a strategy for this, we kind of took 2 approaches, both a top-down, very high-level approach, and then a bottoms-up approach to this. So from the top-down level, this is looking at needs that are really driven by the science that we're doing. That's why we're building the source in the first place, new techniques, new detectors, and especially things we can do with data analysis and AI and ML. But from the bottoms-up perspective, what we did is went beamline by beamline and instrument by instrument, developing detailed plans. So we are anticipating the techniques that will be performed, the detectors that we either already have or intend on purchasing. And from that, we can drill down into the data rates that we're going to collect. But that then drills into more things like the kind of networking that we need, what we need for beamline controls, and what we need for data management and data analysis capabilities. So we anticipate over the next decade, we'll be collecting hundreds of petabytes of raw data per year that require tens of petaflops of on-demand computing just to be able to do first-pass data processing. So this is data reduction, data reconstruction, so our users can then start analysis and interpretation. This necessitates upgrades and capabilities in a number of key areas, and then there's 5 that we've identified in this space. Upgraded network infrastructure within the facility and to computing facilities outside, software that enables adaptive feedback for experiments, expanded capabilities for common data management and data workflow systems, using HPC resources for on-demand computing, and especially developing high-speed data processing and data analysis software, and a lot of focus especially on AI and ML methods, so that we can process data from these newly enabled techniques that are based on high energy, high brightness, and coherent X-rays. So what we've done is compiled all of this information into a computing strategy document you can find using the link at the bottom of the slide. This is a public document that we update on an annual basis. So what I'll do now is kind of talk through each of these areas in terms of what our plans are and the progress that we've made in that space. We are updating the network architecture at the facility. This is what we're actually doing for the entire facility, including the accelerator and storage ring, but we'll just focus on the beamlines here. But we're moving to a 3-tier network infrastructure, the facility as the first tier, the sector as the second, and the hutch as the third. We're adopting in a lot of places what's called a supervisory control and data acquisition architecture, or a SCADA architecture. That way we can better segregate the different types of network traffic and provide quality of service. So keeping the control system separate from high data rate detectors, and then people, beamlines checking their email. We've installed an entirely new fiber plant at the APS. 768 pairs of new single mode fiber. We've installed new core network switches capable of 100 gig uplinks. We're in the process of procuring new tier 2 and tier 3 switches with the same capabilities. And we've also upgraded our network between the APS and the Argonne Leadership Computing Facility, which is our supercomputing facility on campus. Right now it's a 200 gig, but our plan over the next decade is to move this to a multi-terabit per second network. Many of the instruments that we're developing are scanning probe microscopes. Things that require micro and nano positioning. So fast scanning and feedback capabilities and the ability to get data out of detectors is really important for this. So the beamline controls group at the APS has developed a tool called Soft Glue Zinc, which provides configurable FPGA capabilities for data acquisition. And you can see in the schematic, which is for one of our featured beamlines, the in-situ nanoprobe, this allows us to connect fast interferometry to the control system for motion feedback. And this is not unlike what Diamond has developed, the Panda box. In terms of fast detector data acquisition, we do use EPICS at the APS. That's not going to change, but we will be deploying EPICS version 7 and area detector and some newly developed streaming capabilities in the PVA-PY framework that allows us to process and ship data around at thousands of frames per second. And so this is very similar to the kinds of capabilities you'd find in a contemporary message broker system, but for larger data payloads. And near the end, I'll show a video of all of these in action. We are intending to move towards blue sky. I won't talk more about it because Pete gave a really great talk on Monday, talk number 69, about details for that. So I would refer you to that one. We also have a facility-wide data management system, the APS data management system. So these are tools that allow users to automatically transfer data between acquisition systems, computing resources, and storage systems. And as Hannah had mentioned in her talk on Tuesday, we've integrated this now at over 50, I think 53 of the 60-something beamlines we have at the APS. And so this is going to provide the base of data management for our facility going forward. And I would refer you to Hannah's talk for more details about this. So the next item in that list of bullets is what do we do to get our 10 petaflops per second of on-demand computing? And what we're doing is adopting a multi-tiered approach to this of local and then high-end remote compute resources. So the APS maintains a compute cluster. It's about 100 nodes and a number of different GPU workstations. And we'll continue to use local resources like this for things like pre-analysis data reduction, ML inference, so that way we can control the experiment and know we're collecting good data. But for things like large data processing, training large ML models, users coming back and wanting to do post-processing and data refinement, we're going to outsource this to remote computing resources. We're very lucky at Argonne in the sense that we have a large supercomputing center on site. One of the newer machines that will be coming online in the next year that Justin talked about on Monday is Aurora. So this will consist of Intel CPUs and Intel GPUs. It will be probably 2 exaflops per second. It'll definitely be more than 1, but probably around 2. But in the meantime, we're using another system that was recently put into operations this year, Polaris. And there's something really exciting about this for us. Those of you, especially yesterday, there were a number of talks about using large compute resources and some of the challenges with that, right? Usually when you have a big compute center, the goal of that center is to maximize clock cycles. So the resource and scheduling systems on it do the best they can to make sure that you use it all the time. But what this means for an experimental facility is it's not ready and aligned when we need it for an experiment. So about 10% of this new system, Polaris, is actually dedicated so that the APS can prototype using systems like that in an on-demand fashion. And so the goal in this is to really couple that compute with the instruments so they're part of the same system in the same instrument. So what we've been doing with our colleagues in the computing center is testing things like on-demand compute access. So that when we submit a job to the scheduling system, it will kick off something else that's running as like a simulation so that we always have priority. And that so far in testing has been working well. We've been testing things like gateway nodes that allow us to ship data directly to the computer and avoid all the local intermediate IO steps. So as a part of this, we're developing end-to-end workflows so that we can connect all of these high data rate instruments at the APS with the computing system. So this is the first one that we actually put into production use this year, using Polaris for XPCS data processing. So in this case, we move data quickly as soon as it's collected from the 8IDI beamline at the APS to Polaris. The jobs run in about 5 seconds after we submit the command to run it. And then we use a number of tools afterwards developed by our colleagues as a part of the Globus team to ingest this into a web portal so that users have a technique-specific view of it. In this case, a scattering pattern and the G2 correlations for this. So our goal in the long term is to develop portals like this for all of the techniques that we use at the APS. And this will be one of the focuses of our effort over the next couple of years. Of course, if we want to run things on big computers, we need software that can run on them and can scale to that. So what we've done as part of our strategy and planning process is figuring out what are the techniques that actually need high performance computing and then start developing software for that. So we focused our efforts in things like coherent for Bragg coherent diffraction reconstructions, MIDAS for grain and structure mapping, RSMap 3D for high performance reciprocal space mapping. We've recently begun effort on a project called Type for a collection of different typographic reconstruction tools. Over about the past decade, the APS has been developing TomoPi for tomography reconstructions. And more recently, we've been developing GPU code for XPCS correlation software and fluorescence mapping. So this is just a vignette of some of the high priority packages that we're working on, but you can follow the links at the bottom to all of the code that we write at the APS. And we do try to make as much of this as possible open source. So I mentioned a few times already about AI and ML, and this really has a lot of potential to unlock efforts in data reduction, experiment steering, and knowledge extraction as a way to deal with hundreds of petabytes of raw data. So my colleague at the APS, Matthew Charakara, has been working on applying neural networks to a number of different beamline data processing techniques. TycoNN is one of them, which basically trains a neural network for typography reconstructions, and this can be up to hundreds of times faster than using conventional iterative approaches to this. Similar package BraggNN is for peak finding, which is in this case over 200 times faster than using the pseudo-Voigt technique. A group at the APS and our Nano Center has been using Google's OR tools, which are basically tools, if you're not familiar with, that solve the traveling salesperson problem. And they've applied this to actually automate scanning. And so this is a typography scan that reduced motor movement by up to 80%, but still came up with a very good scan profile in terms of maintaining data quality. And then we've been doing things like looking at generative adversarial networks in the cases where we can't collect enough data. So in some cases, we don't want to have, we don't want to damage the sample with too much X-ray dose, or we can't reach a certain angle, so there's an occlusion in it. And so we've been using this to try to explore what we can do for basically filling in the data that we can't collect. So putting all of these pieces together, this is an example of doing that for real-time typography reconstructions. So in this case, for each data set that comes in, some of the initial images that are collected, the initial diffraction patterns, are sent over to the Argonne Leadership Computing Facility, in this case using Theta GPU, and that trains a model very quickly. The model is then deployed locally at the beamline on, in this case, an NVIDIA Jetson edge device. And the new data that comes in for that sample is sent to the edge device for ML inference. And then we can reconstruct that image and stitch it together and show it at the beamline. So these are the kinds of things that we're doing, hopefully, to overcome the large data problem that our facility is experiencing now and is really going to be critical in the upgrade era. So I talked about a lot of technical things in terms of our strategy, but something else that's really important is people and collaborations. And so the APS, along with the other US funded light sources, have joined together in something called the Light Source Data and Computing Steering Committee to basically get together and develop and maintain a strategic plan for all of us in the area of computing. You know, our users, and it's the same with light sources and neutron sources all over the world, usually travel around to different places depending on where they get beam time, right? So it's not a one facility problem. But we've been developing initially in terms of this, we started doing this in 2017. We've developed guidance and reports on data and computing needs, a common data policy template, and right now we're working on proposals that have been funded by our sponsor in the AI ML space. But we're still working, you know, we are working together to try to find other projects that make sense for us to do in collaboration with each other. And even most recently, the APS has reached out to Diamond Light Source and is having a lot of discussions about what we can do in terms of ML for our facilities. So let's see. With that, just to summarize, you know, there's a lot of efforts that we have in scientific computing. Our strategy, though, is based on the strategic need of the facility, what we're doing in terms of science and what the individual beamlines need. Our upgrade is actually going to begin the storage ring replacement in April of 2023. Should take about a year and then into beamline commissioning. So our goals right now critically are really to just keep implementing our strategy and refining it as we see new challenges arise. One more thing, this is just a subset of all of the people at Argonne that have been working on APS problems. So there's probably over 100 people or so that are doing this. So it's not a small issue. You know, we're really grateful for all of the interest and support in this space. So with that, thank you very much. Happy to, if you have any comments.
Thank you, Nicholas. Do we have questions? Yes, please.
How closely do we work with the beamline scientists? The question, yes, very closely, right? I mean, they're in a way the customer for what we do, but I prefer to look at it as a partnership, right? So for each, let's say, of the software toolkits that's up there, there's usually some software engineers, computational scientists, and the actual instrument scientists that are using it, working together as a team to develop it. So it very much is a partnership with them. Otherwise, they're not going to use what we develop, right? Or it'd be a challenge to get for that to happen. Yeah.
Yeah. You plan to treat interactive sessions on HPC during these times?
That's a really good question. So right now we haven't thought about what we're developing are curated workflows for this, right? Not interactive ones where anyone can come and just run an arbitrary piece of code during beam time. And that's a good question. You know, most of these HPC resources do have an interactive mode in it, right? And so we could use that. But most of what we do for some of the high throughput techniques is usually a workflow that is decided with the instrument scientists in terms of what we want to do. So we're going to stick with those at first. But that is a good question of what, you know, if somebody comes with their own code that they want to run, what do they do? Right? That's a good question, though. Thank you.
How does that work budget-wise? So if you, I mean, the upgrade project costs X amount of money, and you happen to have this wonderful high-performance computing facility next door, right? So do you get a chunk kind of pre-allocated there, or how does the accounting?
So that's a very good question. So what we've done, so for the Polaris machine, DOE that paid for this basically made a set aside and said 10% of this will be for work like this. Right. And so we've had a lot of very good discussions with the computing part of DOE recently over the past few years. And I think really done a good job since we came together as 5 light sources to move the needle from, you know, just a big piece of hardware that people use as a big computer to something that needs to be integrated more with experimental resources. And that's a good thing. That's something that's very unique, right? Because on one end you have big simulation. You can go to the cloud for a lot of things, but there seems to be, there's this niche of space that hasn't been looked at. And so our computing part of DOE is called OSCAR, Advanced Scientific Computing Research, has actually become quite interested in this as a thing that they can do to add value for within the DOE landscape. What we do right now as well for our users is we maintain facility allocations for them. So instead of making a user come and apply for computing time and they may get rejected to different group of people, we just maintain that as a facility and they can use our allocation.
Yeah, one more question, last question.
Have you considered to provide your users with some kind of platform to do data analysis remotely?
So that is what we're working towards in terms of the, I probably skipped over this very quickly, but what we're working towards in terms of the web portals for this is something they can log into after the experiment is over as well and see their data. And then ultimately we'd like to put a button on here that says rerun this with new parameters in it.
Okay, then let's thank Nicholas one more time.
Thank you, everyone.